Welcome back. Today we're going to be looking at the last topic in this unit, which is 5.6, problems involving permutations and combinations. So while we're going to be looking at some similar probability questions that we've done before, we're also going to tie in perms and coms. So right off the bat, we're going to take a look at some terminology that we've already been using up to this point, just as a quick refresher. So when we did the permutations and combinations unit, we talked about the fundamental counting principle. So an example might be if I have 3 books and I'm arranging 3 books on a shelf, I have 3 choices for the first spot, 2 choices for the second, and 1 for the third. So fundamental counting principle, multiplying our choices by our choices by our choices. So order matters. We looked at factorial notation, which we're not going to be working with too much today. We had the formulas for permutations and combinations. Big piece there is that permutations order matters and combinations order does not matter. So notice that for permutations order matters and combinations order is not important. When we deal with questions that involve repetition, remember that we have to divide by our repeats. And then when we're talking about probability, we're talking about our total favorable over our total possible. Now, when we're working with permutations and combinations, it's really important that we deal with our favorable and our total separately. So figure out what our favorable is, figure out what our total possible is, deal with them separately, and then combine them into the probability fraction. When we're doing these questions, it's important that you read very carefully. So ask yourself, is repetition allowed? Because that'll change how we do the question. We still deal with the restrictions first, just like when we were dealing with permutations and combinations. And it's really important that we ask ourselves, does order matter? All right, so let's take a look at some questions. Now, as we work through some of these, you're going to find that some questions can be done in multiple ways. They can be done with perms and coms. They can also be done just by using our formulas. But anytime we start to actually talk about selecting and arranging, we need to go with perms and coms. So the first example here, it says 2 cards are selected without replacement. So without replacement is important. So 2 cards are selected without replacement from a deck of 52 playing cards. And the question says to determine the probability that both cards are jacks. So we're looking for the probability of a jack and a jack. So without replacement means this is a dependent scenario. Because we're not replacing them, our card total will change from the first pull to the second. So the probability of getting a jack and a jack, we have 4 jacks out of a deck of 52 cards. We're not replacing the cards, so assuming we get a jack the first time, we have 3 jacks left to pull from, and there are only 52 cards in the deck. If we multiply that and reduce it to lowest terms, we get 1 over 221. Now we can also do this with combinations. So we have 4 jacks in the deck and we want 2 of them. So 4 jacks and we want 2 out of 52 cards and we're pulling 2 cards. And so this will also give us 1 over 221. So the top part is our favorable. Our favorable, we want 2 jacks, and so that's 2 jacks out of a possible 4. When we're pulling the cards, order does not matter, so it's combinations. And then if I was just looking at all the different ways that I could pull 2 cards out of a deck of 52, it would be 52 choose 2. All right, let's take a look at the next example. So example number 2 says the current format for newly issued Alberta license plates is ABC-1234, starting with BBB000. So we don't have any A's, and we're told that vowels are not allowed. So vowels are not allowed, so we can't have A, E, I, O, or U. That means that we have 21 letters to choose from. So the question here says, what is the probability that someone would get license plate BTW 8688? Well, the probability of getting BTW 8688 is going to be 1 out of the total possible combinations. And so if we look this up, or if we use the fundamental counting principle here, we have 3 letters followed by 4 digits. Now, these 3 letters cannot be, so it can be any letter except A, E, I, O, and U. And then these here can be anything from 0 to 9. Now notice we've got an 8, 6, 8, 8, so that shows us that repetition is allowed. And so there are 21 letters for the first choice. And we also had this B, 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 so that also tells me that repetition is allowed. So we have 21 letters for the first choice, 21 for the second, 21 for the third. We're multiplying. And then there are 10 choices, 10, 10, and 10. And if we multiply that out, that gives us 92,610,000. Now, if we're looking at our probability, the probability of getting that license plate is 1 out of 92,610,000. All right, part B says, what is the probability that someone would get a license plate that starts with BTW? Well, if it starts with BTW, there's only one choice for each of my letters, and then I still have the 4 digits afterwards. So this has to be a B, this has to be a T, and this has to be a W, and then these numbers here can be anything from 0 to 9. So we're going to consider our possibilities. We know from the previous question that there's 92,610,000 ways to rearrange those license plates. What we're figuring out is how many license plates start with BTW. And so there's one way to have a B, one way to have a T, one way to have a W, and then we've got 10, 10, 10, and 10 choices, which comes out to 10,000 over the total possibility, which is 92,610,000. If we reduce that to lowest terms, it's 1 over 9261. All right, let's look at how this plays out with cards. So this question here says, in a card game, you're dealt 5 cards from a pack of 52. So we're getting a 5-card hand out of 52 cards. And when you look at your 5 cards, we want to know what is the probability and expressed in combination notation. So what is the probability expressed in combination notation that you have 4 aces? So just like we had here, we're going to deal with our total possible and our total favorable separately. So the chance of getting 4 aces, well, that means 4 aces and 1 non-ace. So there are 4 aces in a deck. We are choosing 4 of them. And that leaves us with 48 other cards, and we're going to choose 1 of them. That's our favorable scenario. This is the likelihood or the situation where I would have 4 aces and 1 non-ace. Now, that's over a total possible. Well, the total possible is just having 52 cards and choosing 5 of them. So we're not going to reduce these, we're just going to leave them in combination notation. All right, the next one says 4 tens and an ace. So we want 4 tens and 1 ace. Well, there's 4 tens, we're going to choose 4 of them. And there are 4 aces, and we're going to choose 1 of them. Again, out of the total possible, 52, choose 5. Next question asks us to look at the probability that we would get a 10, a jack, a queen, a king, and an ace. Well, for 10, there are 4 tens. We're going to choose 1 of them. For jack, there are 4 jacks. We're going to choose 1 of them. For queen, there are 4 queens. We're going to choose 1. Kings, there are 4. We're going to choose 1. And aces, there are 4. We're going to choose 1. So it's really 4 choose 1 to the exponent of 5. And then again, out of the total possible, 52 choose 5. So you might see this written as 42 choose 1 to the exponent of 5 all over 52 choose 5. All right, now our last question says, what's the probability of getting at least 1 king? So that's 1 king, 2 king, 3 king, 4 king, or 5 king. Now that would be a lot to write out, unless you remember that at least also can be used, or we can use the complement to solve for at least questions. So we can go 1 minus the probability of getting no kings, because the opposite of getting at least 1 king is getting no kings. So we're going to go 1 minus the probability of no kings. Well, no kings would be 4 kings choose 0 times 48 choose 5. Now the 4 choose 0, if you remember, that equivalent or equates to 1. So you don't have to write that part down, but it helps to check your totals again. So we've got 4 choose 0. We've got 4 choose 0 times 48 choose 5 all over 52, choose 5. So if we write that in simplified form, we're going to have 1 minus 48, choose 5, all over 52, choose 5. Now, when it comes to these types of questions, there are so many different examples I could give to you. I'm just going to be giving you a handful of them today, but it might be important to look through some of the practice questions because, again, there's so many different ways that you can be asked these questions. So example number 4, it says the word counted has been spelled using Scrabble tiles. 2 tiles are randomly chosen one at a time and placed in the order in which they were chosen. You're asked to determine the probability that the tiles are CN. So when we're looking at this, we want it to be in the order CN. So in this case, order matters. And so we're looking at the probability of getting CN. Well, there's only one way I can have CN, but how many ways can I choose those tiles? I've got 1, 2, 3, 4, 5, 6, 7 tiles. Because order matters, it's a permutations question, and I'm going to take 2 out. And so the probability of getting CN is 1 way out of 7 pick 2, which can reduce to 1 over 42. Now, we can also do this question another way. We can use the fundamental counting principle. We can look at this and say, well, wait a minute, we have 7 ways that we can pick the first letter, and we've got 6 ways to pick the second letter, so that's 42, meaning there are 1 over 2 ways. So we can also use fundamental counting principle. Now, what if we're looking at the probability of getting both vowels? So both vowels. Well, there are 1, 2, 3 vowels in there. So that means that we have 3 vowels. I want to pick 2 of them out of 7 letters, picking 2. Reducing that, we have 6 over 42, which equals to 1 over 7. So this means my total possible is just 7 tiles, and I'm picking any 2. Order matters, so it's permutations. And then what I want is 2 vowels. Well, there's 3 vowels, and I'm going to pick 2 of them. Again, I can use fundamental counting principle for this. I can take the bottom part, which is 7 times 6, and on the top, I have 3 choices for the first vowel times 2 choices for the second vowel. So that leaves me with 6 over 42, which reduces to 1 over 7. Example number 5, Darian's smartphone contains songs. If he listens to 10 songs on random, determine the probability as a percentage to the nearest hundredth that the playlist contains his favorite songs. So now we've talked about playlists before where order matters if we're actually doing it for a dance and we have to play specific songs, but we're told here that we're just playing the playlist on random. So that tells us that order doesn't matter. And so we're looking at the probability that Darian is going to play his 2 favorite songs. So out of those songs, we have 2 that are his favorites and he wants both of them. So order doesn't matter. We use combinations. And then that leaves us with 48 other cards. Or sorry, 48 other songs. Sorry, not cards. 48 other songs, because remember he had, I missed writing the 50 in here. There's 50 songs. Okay, so his smartphone contains 50 songs. If he has 2 favorites, that leaves us with 48. Choose 8. So notice the 48 and the 2 have to add up to 50, and the 2 and the 8 have to add up to 10. So I was just missing the 50 in the question. Now, that's how many ways he can have his 2 favorite songs, but if we're just looking at how many ways we can have 10 songs in our playlist, it's 50 choose 10. Now, if we put this into our calculator, we're going to be aware of using brackets throughout. We're going to get 0.03673, but we're asked to represent this as a percent, so we multiply by 100, gives us 3.67%, which is to the nearest hundredth. Now, for the second question, it says that one of his 2 favorite songs is at the beginning and the tens of the 10 songs and the other is at the end. So now we're looking at order mattering because there's a specific position that we need for his first favorite song and his last favorite song. And then in between, those songs are being arranged. So any 8 in order. And so we're going to have, for his first choice, for his first song, there are 2 choices. For his second song, there's one choice. And then inside here, we're going to have 8 factorial or 48 pick 8. Oh, sorry, not 8 factorial, I apologize. We would have 48 times 47 times 46 and so on. So we're going to have 48 songs and we are picking 8 of them. So what we want is 2 pick 2 times 48 pick 8. And that's all divided by our total possible, which is 50 songs, pick 10. And so the order matters because we're told specifically where certain songs have to be. So 0.000816 equals 0.08. Now, if you look at these 2 questions, they look very similar at a glance, and possibly after we go through them, it's a little more obvious that one's order matters and one isn't. But when you're doing these on a test or on a review, sometimes you just got to look for those keywords, and then also just think logically, is this something where order would matter? Is this something where order would not matter? All right, example number 6. So it says city council consists of 9 men and 6 women. 3 representatives are going to be chosen at random to form an environmental subcommittee. So typically subcommittee order doesn't matter, but when we start getting into positions and executive subcommittees, then order would matter. So the question says, what is the probability that Mayor Ted Clugston and 2 women are chosen? Well, we're going to start off by asking ourselves, does order matter? We're just looking at a committee, so order does not matter. It doesn't matter who's on the committee or in what position they're chosen to be on the committee. It's just that they are on the committee, so order does not matter. All right, so we have 1 Ted Clugston, and we want to choose him to be on the committee. And it says, what is the probability that Mayor Ted Clugston and 2 women are chosen? Well, we only have 6 women to choose from, and we're going to choose 2 of them. Now, that would mean that there are 8 remaining men, and we are going to choose 0 of them. So we still have 9 plus 6 being 15, and 8 plus 6 plus 1 is also 15. Typically, you won't see this 8 choose 0 written because it just totals to 1. Now, our total possible on the bottom is having 15 committee members and choosing 3 of them. So if we reduce that into lowest terms, we get 3 over 91. Now looking at the second question, it says, what is the probability that 2 women are chosen if Mayor Ted Clugston must already be on the committee? Again, these look like very similar questions. One is looking at the probability of Ted Clugston and 2 women. The other one is asking about Mayor Ted Clugston and then just 2 women chosen from the remaining people. So if we were to reword this, this is Mayor Ted is already on the committee. And we have to choose 2 women from remaining 14 people. So here we have Ted Clugston on, and we're choosing 2 women. Here we just want the probability that 2 men are chosen if he's already on the committee. So if Mayor Ted Clugston is already on the committee, there's only one way that can happen. And then we have 14. On the bottom here, we have 14 people choosing 2. So we're choosing 2 committee members. But on the top here, of those 6 women, we're choosing 2 of them. So you could have also written it this way, 1 choose 1 times 6 choose 2, out of 14 choose 2. Now notice this is 15 choose 3 and this is 14 choose 2, because for the first one, we're just looking at the probability of him being on the committee. For question B, he's already on the committee, so that leaves us with less people to pull from. Putting that in lowest terms, we would have 15 over 91. And our last example, it says that a hacker is attempting to break into a friend's security protected file. The friend tells the hacker all the numbers that are in the 4-digit PIN, but not the order or how many times each digit may be repeated in the PIN. So we don't know we don't know the order, and we don't know how many times they're repeated. So we're going to figure out the probability that the hacker correctly guesses the 4-digit PIN on the first attempt if the friend tells her that the PIN contains 2, 3, 4, and 5. All right, so if we have 2, 3, 4, and 5, then that means there are 4 factorial ways to rearrange those letters. So we've got 2, 3, 4, 5. There are 4 factorial ways to arrange those letters. There's only one pin, so the probability of being successful is 1 over 4 factorial, which is 24. Now, what if we're told there's only a 2, 3, and 4 in here, but it's a 4-digit pin? 4-digit pin means we either have repeating 2s, so we've got 2, 2, 3, 2, 2, 3, 4. We could have a 2, 3, 3, 4, or we could have a 2, 3, 4, 4, because we still have to have the 2, 3, and 4 in there. So looking at these scenarios, if we look at the first one here, we have repeating 2s. So there are 4 factorial ways to rearrange these. Divided by the 2 factorial repeats is 12. 4 factorial divided by 2 factorial is 12. And 4 factorial divided by 2 factorial is 12. So if we look at that, there are 36 different possibilities, and we've got a 1 in 36 chance of guessing the correct pin. All right, let's take a look at the scenario where only the numbers 2 and 3 are included. So if we only have a 2 and 3 included, that means we can have 1 2 and 3 3s. We can have 3 2s and a 3, or we can have doubles and doubles. Well, looking at this first scenario, there are 1 2 3 4 numbers, but we have 3 repeats, so that gives me 4. We have 4 numbers with 3 repeats, gives me 4. And then we have 4 repeats divided by, 4 numbers divided by the 2 repeating 2s and the 2 repeating 3s, gives me 6. So if I total that up, there are 14 arrangements. And of those 14, there's only one possible correct pin. So I've got a 1 in 14 shot. So notice having the 3 numbers puts us at the most possibilities, so less likely for someone to get our pin. So when we're talking about hackers and we're talking about people recommending what our pins should be, they're doing these calculations to figure out what the likelihood is of a computer figuring out our passcode. Now, let's ask one more question here. What if the person tells them there's only a 2? Well, this should be an obvious question. If there's only a 2 in my pin, well, then my only option is 2, 2, 2, 2. And so 4 factorial ways to arrange them divided by 4 factorial. There's only one possible combination, so we've got a 100% chance of getting our pin. So definitely don't use just one number in your pin. All right, like I said, there are so many examples I could give you for permutations and combinations. Within the practice questions, there are lots of variety as well, so I would encourage you to try some of them. But feel free to come and ask questions, and have a good night, and we will see you soon.